All right, on this problem, we want to find dy, and so what we're going to do is we're just going to harken back to those times when we were talking about different ways that you could write a derivative. You could say dy dx, you could say f prime of x, you could say f prime, you could say y prime, you could say d dx. These are all different ways to just show that you're involving a derivative in whatever it is that you're doing. So if we're going to find dy, we're going to use this first guy right here. He's the guy that we want to use. So over here with this function, dy dx is going to be 1/2 6x plus 8 to the negative 1/2 power. I have no idea what that little dot is right there. I don't remember putting him up there. I'll just get rid of him for you OCD kids. And then simplify this down just a little bit, not a whole lot. You know, you're going to have 1 over, now watch, the hand is quicker than the eye, 2 square roots of 6 plus 8. Wow, that's a bad 6. 6x plus 8. Wow, here we go, 6x plus 8. And also don't forget up here, I forgot my little chain rule part. Derivative of the inside is 6. So this would be 6 over that. And that's what dy dx equals. Now, to finish this problem up, we would go ahead and reduce the 6 and the 2 and multiply by dx. So we'd multiply this side by dx, and we'd multiply this side by dx. And so I end up with dy equals 3 over square root of 6x plus 8 times dx. Or if you wanted to, like, if you want to be like a cool person, we could say this. We could say 3 dx over 6x plus 8 to the 1/2. Both of these are equal. They both say the same thing. They're both good answers. All right. So that's how you find dy. The change in y as it directly is related to the change in x, exactly what that relationship looks like. All right, here we're going to use the change in the function and look at the change in x and kind of compare it in actual slope form, what is actually going on, what's the estimated change or the true change or all that kind of stuff. And these numbers should be really, really, really close. When you get done doing all your math, you should have several decimal places that match, okay? What we've got to do though is we've got to find it. We're going to need a derivative in there at some point, so we're going to go ahead and do that right now because we have to use it. So f prime of x is equal to 2x minus 1. And then just follow your formula here. I've given the formula to you on this problem. So the formula says f of a plus dx. Here's a, so a plus dx would be 5 plus 0.04 or 5.04. All right. And then f of a, we need that. So f of 5, that's going to be 25 minus 5, which is 20. Okay. So that's this part here in this kind of bluish color. All right. So let's go ahead and work that out. F of a plus dx minus f of, so here's what we're going to have. We're going to have f of 5.04. And when you work that out, you're going to end up with, I get 20.3616. Punch it into your calculator. Unless you want to square out 5.04 by hand. And then knock your socks off. That's good practice. It's good practice. So when I do all of this in blue, I'm going to do my f of a plus dx 20.3616 minus 20. And so I get a change in f. In other words, how much my y value changes because my x value changed by 0.04. I have that much error. My y value then has error or a change of 0.3616. Okay. We could look at it then with the estimated change, which is f prime. Let's do it in this other color. F prime of a at dx. And so here's f prime right here plus a, f prime of a. So that's back to we're going to look at f prime of a times dx. So times 0.04. Again, you'll want to punch this into your calculator. So in other words, what I'm doing is I'm doing 2 times 5 minus 1. No, that was right. Yeah, minus 1. And whatever answer I get in there, I'm going to multiply by 0.04. So what is that? 9 times 0.04, which is going to be 0.36. So notice those numbers are really similar. They're not 100% exact. Our actual true change carried out a couple more decimal places than our estimated change did, but look how close they are. So if we had some sort of change in x that was larger or had more decimal places, then we would have more decimals on our derivative part on our estimated change. But the point here is both of these are so similar that if you just look through the hundredths spot, they're identical. But that's how you use these two formulas here to look at true change and estimated change. Alrighty, here are a few related rates questions, and I've always liked related rates. I'm not sure why. They're like puzzles. You have to figure out how they all go together and take a derivative and find out what you have or don't have. I just like them. They're fun. So here we go. A man flies a kite at a height of 120 meters. The wind carries the kite horizontally away from him at a rate of 8 meters per second. How fast is the distance between the man and the kite changing when the kite is 130 meters away from him? So, you know, coming from Oklahoma, it's not hard to imagine a nice windy summer day that we could be off flying our kite. So let's go ahead and fly this kite. And I'll use some really straight lines. So here we are holding the string, and I don't want that color, so let's have blue string for a blue kite for a blue sky. So here's the kite, and he's holding it. I know we don't want to be too picky. We don't know how tall he is, but we'll go ahead and say that he's 0. So our triangle that we're creating with that kite looks something like this. This might not be 100% perfect, but it's pretty close. And up here we have a kite flying in the breeze away from the man. So here's our kite. There it is, right on that corner. And what we know about this kite is that it's at a height of 120 meters. So this side right here has to be 120. And we know that the rate of change between the man and the kite, oh, well, let's see. We don't know that. So that would be a change in this hypotenuse. That's change in rate. So dz dt we don't know. The 120 meters is how high he is. We'll go ahead and call that y. And the 120 meters doesn't change. So dy dt, just for reference here, is going to be 0. Because remember, dy dt represents change, and if we're always at 120 meters tall, then we're always at 120 meters tall. No change, no derivative, okay? Or 0 derivative. And then at the exact instant in time that we're curious here, we know that the kite is 130 meters away from him. So we know that up here, this distance, we'll call it z, is 130 meters. So the only thing we don't know down here is x. And we do know, though, from our problem, the rate of change of x. We don't know what x is, okay? But we do know that the wind carries the kite horizontally away from him at a rate of 8 meters per second. So the change in rate for x is 8 meters per sec. And now I'm ready to go. I've got all this information set up. So what can we do? What formula can we use? I've got a model here that represents my situation from my word problem. So what thing relates x, y, and z together? I'll let you think for a minute. Go ahead and think while I write. I won't even say what I'm writing. And while you're thinking, I hope you're thinking what I'm writing. Okay, Pythagorean Theorem. Now, do we know what x is? We don't. Dadgummit, we don't know what x is, but can we find x? Yeah, we sure can. We've got Pythagorean Theorem going on here. So x would be the only piece that we're missing. So how do we find that? Well, x is equal to the square root of the hypotenuse squared, which is 130, minus one of the legs, which is 120, not degrees, squared. And if you punch this into your calculator or simplify it out or work it out or however you want to do it, you should wind up with x being equal to 50. So now I've got everything I need to solve this problem out. I've got x, y, and z. I've got change in x. I've got change in y. Change in z. This is the one that I'm interested in. We want to know, what is that guy? So let's look at this equation, Pythagorean Theorem, which relates everything together. We're going to look at this relationship as a function of time, which means that when we take a derivative, we're going to add a t in there. So how does this work? Well, I'm going to take the derivative of 2x, and then I'm going to chain that with dx dt, because x is not my independent variable now anymore. Okay, the t is. Plus 2y times dy dt equals 2z times dz dt. All right, we've got everything here except dz dt. So substitute in your values. We're going to have 2 times 50 times 8 plus 2 times 120 times 0 equals 2 times 130 times dz dt. And work that out. 2 times 50 times 8, that's going to be 800, plus 0 equals 260 dz dt. And how do you get dz dt all by itself? Divide by the 260, because basically that 0 doesn't exist. So 800 divided by 260 is equal to 3.077 meters per second. Okay, and think about it. Does that make sense? Is that something that sounds logical? Well, remember, it's blowing away from him at 8 meters per second, and this is up in the sky, going away, up and away, away, horizontally. And so, yeah, this is something that could work. And there you go. There's a related rates question with the old sky flying kite. And this is one of those questions that you may need to work again on your own. So I would suggest pause the video, turn over a fresh sheet of paper, and see if you can get the same answer I did without coming back and looking. All right, a 6 foot tall, that should be a 6 foot tall man, walks at a rate of 2 feet per second away from a lamppost that is 13 feet high. At what rate is the length of his shadow changing when he is 35 feet away from the lamppost? So again, what we want to set up here is a situation where we've got a right triangle, and this is going to be solved out a little bit differently than our other right triangle problem. So I don't know if this is 100% perfectly right for those of you that have some OCD issues, but there you go. Okay, right triangle. Let's label off what we know. We know that this lamppost right here is 13 feet high. So here's 13 feet, and you know, if you want to add the little lamppost thing right here to give it some character, you know, so that we know what we're looking at, go ahead and there we go. Bright light, lamp shining into the dark. Okay, and then we've got this guy who happens to be 6 feet tall right here, walking along, minding his own business, maybe. And we know that he's 6 feet tall, so we'll label him. Oops, we don't label him with one of those. He's 6 feet tall. And we're just I'm gonna label some stuff here. I like to call things that go up and down Y. I like to things that go left and right X. And in this case, we're kind of splitting this X axis up into 2 different pieces. So I'm just gonna call this other guy over here Z. Okay. Now, so we've got these different pieces here. Again, with dy dt, whoops, that should be dy dt. dy dt is going to be 0, okay? Because the length of the lamppost above the ground does not change. It stays at 13 feet. So there's no change. If there's no change, there's no rate of change. If there's no rate of change, it's 0. dx dt is how quickly we are approaching the lamppost, and it told us that a man is walking at a rate of 2 feet per second away from a lamppost that is 13 feet high, which means that he's walking this direction. So that's going to be positive 2 feet per second away from the lamppost. Okay, and then lastly, we want to know how his shadow is changing. So that's this guy right here. That's dz dt. We want to know, this is our question. How is this guy changing? Okay, so we've got to figure out a way to relate all this stuff together. And by the way, we know that x has to be 35 feet. All right. What I would recommend is a triangle comparison. Big triangle here, big here. See it, see it, see it? Big triangle here. Let's compare the two legs to each other. And if we compare those two legs to each other, we would get that x plus z over 13. And then if we compare it to the shorter, smaller triangle in here, which is right here. Let's see, let me get a good color. Right here, here's a shorter triangle right here. See the shorter triangle? So we're going to compare the bigger triangle to the shorter one with legs. And so this is actually going to be z over 6. Okay, and so here's an equation that relates both of our pieces that we need to have. And so here's the equation that we're going to use. So go ahead and start cleaning this guy up a little bit. Let's see. I'm going to cross multiply, so 6x plus 6z equals 13z. And I'm going to go ahead and move the z's to both sides. So 6x equals 7z. And then take derivative. So this will be 6 dx dt. The derivative of x is 1. We're looking at the rate of change over time. On the other side, we're going to have 7 dz dt. The rate of change for this guy. How is our shadow changing? And this is the one we're interested in right here. And then substitute in our values. So 6 times 2 equals 7 dz dt. And then divide both sides by 7. And when you do that, you're going to get 12 over 7 is equal to dz dt. Now, if we're talking about rate of change, if you told me that you were traveling 130 divided by 2 on the way home from school, miles per hour, I would have a really hard time with that. But if you told me you were traveling 65 miles per hour, well, that I understand. So if you tell me that he's walking away from the shadow is changing at a rate of 12.7 or 12/7 whatever's, I don't know what that is. But if you were to tell me the rate is changing, the shadow is changing at 1.743 feet per second, I know what that is. Okay, so both of these are, 12/7 is not incorrect. Don't get me wrong. I just don't have a grasp of how quickly that changes. I know it's going to be bigger than 1, but not quite 2. However, 1.743, I know that's a better ballpark of rate of change for this particular problem. So anyway, there you go. The old man walking away from the lamppost problem. Everybody gets to do one of these. It's always there in your calculus. So there you go. Enjoy. All right, finally, our last problem from the review here. A piece of land is shaped like a right triangle. Yes. 2 people start at the right angle at the same time, walking at the same speed along different legs of the right triangle. Spraying the land. So if the area covered is changing at 5 meters squared per second, how fast are the people moving when they are 5 meters from the right angle? Now, good thing here about this problem is both people are moving at the same rate, which means that their rate is changing at the same rate. and it means that they're going to be the same distance from that right triangle corner at the same time. So this problem got infinitely easier for us when everything became equal. So let's just go ahead and figure out that right triangle. And I'm sorry for you OCD kids if this isn't perfect. You know, none of us are perfect. All right, so we've got this right triangle right here. And we don't need that guy anymore. We need that guy. Right triangle. And we've got a person. Let's call it K-Steve. She's right here going this way. We've got another person. Let's call them Hazelwood Math. They're right here. They're going that way. And so, again, keeping with kind of how we've set all these problems up, let's refer to this as y, and let's refer to this as x. Okay? So, if we're going up and down, we're talking about a rate of change dy dx. If we're going left and right, we're talking about a rate of change dx. Whoops, this should be dy dt. dy dt and dx dt. All right, so these are the things that are happening. Now, here's our clue. Area. Now, how do you find the area of a triangle? Well, the area is 1/2 the base times the height. And we know that dA dt is equal to 5 meters squared per second. Okay? So now we have to figure out how all this goes together. Well, we're told that two people start at the right angle at the same time, walk at the same speed on different legs. So what we know from that is that x equals y. So this problem then changes just a little bit, and we're actually going to use a equals 1/2 x times y. But we just said x and y were the same, so we're actually going with a equals 1/2 x squared. Okay, so this is the model right here. This is the equation that we're going to use from the model that we developed to kind of represent our situation. So I'm going to go ahead and take derivative. By the way, one other last piece of information that we need to keep in mind is that dy dt is the same thing as dx dt. Remember, those are equal because that's the rate of change that we're walking away from the corners, and those rates have to be the same. So let's take derivative of this guy, and he's really not that hard. We're going to have dA dt is equal to, well, 2 times 1/2 is 1. So 1x dx dt. Okay. So how is this going to work now? Well, we were told that we are 5 meters from the right angle. Okay, so we know then that x is 5. Well, if x is 5, so is y. So then all I got to do is plug in my 5 right here for this guy. And oh, by the way, I've got the area. So what's this going to look like? Well, I put in my 5 for my change in area. I put in my 5 for my distance from the origin, basically, from that corner, dx dt. Well, dx dt is what I want to know. Dx dt, this is what I want to know. Okay? dy dt, this is what I want to know. So just divide both sides by 5, and you end up with 1 equals dx dt, which also equals dy dt. So what's the rate of change for this guy? Well, when you take meters squared per second and you divide by a meter, you're going to end up with 1 meter per second. So there you go. Another related rates problem. Just take a deep breath, relax, and they're all 3 of these related rates problems are a little bit different. They all 3 involve triangles. Not all of them do. These 3 do. But just take a little breath. Pause, rewind the video a little bit, see if you can answer this question on your own. If you can't, fast forward to where you're stuck, get a good explanation, try again. And eventually you'll start seeing some of these patterns that develop as far as how to solve these problems. They're all different, they're all unique, but they can all be solved with a little practice on some others first.